Hello everyone, in this video we are going to talk about 3 different ways that we can use to build our TensorFlow models. The first method is to use TensorFlow's keras.Sequencial model. The second method is to use TensorFlow's functional API. And then the third method is through subclassing. So let's get started. We can use keras.Sequencial model whenever our layers inside our deep learning model are placed in a simple sequential order. If we want our model to be more flexible, for example, if we want our model to have multi-input or multi-output, then we need to use TensorFlow's functional API. So when we are talking about functional API, we will go through each topic that I listed here and then build an example model. So first, we will see how we can replicate the simple sequential model that we just built when we were using keras.Sequencial model. And then we will talk about how to use functional API to build branched layer model, to build residual net, multi-input model, multi-output model. And then lastly, we are also going to see how we can use functional API to extract partial model from an existing larger model. And then as a side topic, we will also see how to use functional API to do transfer learning. Lastly, we will introduce subclassing. So when we are building model with subclassing, we got all the benefits of building model with functional API, but we also got all the benefits of creating our model under an object-oriented programming environment, meaning that we can create new attributes to our model and create new methods to our model. Throughout this video, we are going to use the MNIST Dataset as our example datasets. The inputs to the MNIST datasets are 28 by 28 grayscale images of handwritten digits. On the bottom of the slides, I have shown 9 different sample input images from the MNIST datasets. And then the output are simply the integers that corresponds to the input images, which ranges from 0 to 9. And because this is a classification problem with 10 different classes, as you will see later when we go through the code, the first thing that we need to do is to process the outputs by doing one-hot encoding and convert each integer into a row vector of size 10. We are going to first use the keras.Sequencial model to build a simple sequential model for our MNIST dataset classification examples. Also, by the way, throughout this video, for simplicity, I'm going to use just the dense layer or fully connected layers. And because I'm going to use dense layer and fully connected layer, when we feed the images into our model, which is a 28 by 28 images, we need to first go through a flattened layer, which will convert the images into a vector of size 784. And then we will go through 4 different dense layers in a simple sequential order. Lastly, we will have a classification layer. This classification layer is also a dense layer, but the output is restricted to be size 10 because this is a classification problem with 10 classes. Now let's go to Jupyter Notebook and see how we can use keras.Sequencial model to build a simple sequential TensorFlow models. The first thing that we need to do is import relevant libraries. And then we need to use this MNIST.load data to load the MNIST dataset. It will return the input for the training set, output for the training set, input for the testing set, and then output for the testing set. If we check the data type, we can see that they belongs to NumPy array. We can also check the shape of each NumPy array. And from here, you can see that in the training set, we have 60,000 images. And in the testing set, we have 10,000 images. As I mentioned before, the first thing that we need to do is to perform one-hot encoding on the output Y. So this cell is basically doing that. Now let's see how we can build a model. The first thing that we need to do is instantiate an instance of this keras.Sequencial model, which I am naming it to be simple sequential model. Once we have this instance, we can start adding layers one after one. So as I mentioned before, the first layer is the flattened layers. And because this is the very first layer in the model, we also need to have the input shape, which is 28 by 28. I'm giving this layer the name flatten. This is optional. If we don't specify a layer name, then TensorFlow will automatically assign a default name. And then I'm going to keep adding 4 different dense layers. Each one will have a ReLU activation functions. And then lastly, we will have a classification layer with only 10 neurons. The activation function will be softmax. After these few lines of code, we have successfully created a simple sequential model. Once we create this model, we can use this .summary to output a summary table from this model. So inside this summary table, we will have the output shape for each layers, and then also the number of parameters for each layers. At the end, we will have a statistic of the total parameters, trainable parameters, and then non-trainable parameters. Also, you can use this keras.utility.plot model to output a schematic representation of our model. Note that in order to have this .plot model to work, you need to also install PyDot and this GraphViz libraries. To install PyDot, we will need to use pip install PyDot, and to install GraphZ, please use conda install GraphZ. What happens is that if we use pip install GraphZ, then the GraphZ will still install, but however, this keras.utility.plot model still won't work. So just make sure that to use conda install when you are installing this GraphViz library. Okay, so by calling this .plot model, you can specify whether you want to show the output shape or input shape, whether you want to show the data type in your output, or whether you want to show the activations. Over here, I'm setting all of them equals to true. As you can see here, we first have our flatten input, and then it goes through the input layer. It goes through 4 different dense layers, and then lastly, it goes to the classification layer. If we don't specify those options equals to true, then by default, they are equals to false. And as a result, you will get a much simpler schematic illustrations. After we build the model, we can also compile the model by specifying the optimizer, the loss functions, and the metrics that you want to see. After compiling the model, we can also train the model by calling these .fit methods, and we need to pass in the input data, the output data. This validation data is optional, but if you want to see the loss functions and your metrics from the testing data, then you can pass in your testing data into this validation dataset. You will also need to specify the number of epochs and the number of batch size. Next, let's see how we can use functional API to recreate the simple sequential model that we just developed. The first thing that we need to do is create this keras.input object by specifying the input shape. In our case, the input shape is 28 by 28. Again, this name is optional, and I'm calling this object as inputs. The next thing that we need to do is feed these inputs as the input to the flatten layer. To do that, we will first call the flatten layer, open and close parentheses, and place the inputs in between the parentheses. The output of the flatten layer, I'm calling it to be X for now. So next, we need to treat this X as the input to the next dense layer. We can do that by first calling the next dense layer, open and close parentheses with X in between, and then the output will be the new X that overwritten the old X. This new X will again be the input to the next layer, and so on. And then finally, the output of the 4th dense layer will be the input to the last classification layer. The final output, I'm calling it as outputs. So these few lines of code specify the set of operations in our deep learning model. Once we specify this set of operations, the very last step is to call this keras.model, specifying the input parameters, which is the inputs, and then the output parameters, which is the outputs here. And then give this model a name, which I'm calling it functional underscore API underscore model. This is how easy we can use functional API to build a TensorFlow model. Once we build a model, we can check the summary table just like what we did before. We can also plot the model by using these .plot model methods. We can also compile it and train it just like what we did before. And then once we train the model, we can predict it as well. This slide is a schematic representation of the simple sequential model that we just developed. So it's a simple sequential model with all the intermediate outputs equals to x. This x just keep updating after each layer. The inputs will just be inputs and then the output will just be the outputs. Next, we are going to see how to use functional API to build a branch layer models. So for these specific examples, the inputs is going to fit into the flattened layer, and then we are going to create two copies of the outputs. They will be both named x, but one copy will fit into dense layer number 1. The output, I'm going to name it x_branch1, and then it will go through dense layer number 3, and the output will be x_branch1 again. Another copy will go through dense layer number 2, and then its output will be x_branch2. It will then go to dense layer number 4. Again, will create x_branch2. Finally, the x_branch1 and x_branch2 will combine and then fit into the very last classification layer, which gives our outputs. Next, let's go to the Jupyter Notebook and see how we can use functional API to create the branch layer that we just talked about in the slide. We just need to follow the same naming conventions. The inputs will be fit into the flattened layer, which will create an output x, and we are going to create two copies of the x. First one will be fed into dense layer number 1. Second x will be fed into the dense layer number 2. The output from the dense layer number 1 will be x_branch1, which will then be fed into dense layer number 3. The output from the dense layer number 4 will be x_branch2, which will be fed into the dense layer number 4 and create a new x_branch2. Lastly, we are going to perform element-wise additions on x_branch1 and x_branch2, and then fit this entire summation as the input to the last classification layer and produce the final outputs. So after specifying these operations, we can call the keras.model to create a model by passing the input parameters and the output parameters. Over here, I'm naming this model as functional API branch model. Once we create this model, then we can again call the summary to output the summary table, and then call this plot model to output the schematic representation of the model. We can also compile the model and train the model. In this example, we can perform element-wise addition between the output of dense layer number 3 and the output of dense layer number 4 because they happen to be the same shape. In many cases where they are not in the same shape, then we cannot do these add operations on the two outputs. In that case, we will need to simply concatenate them. So we are going to feed the combined output of x_branch1 and x_branch2 by packaging them inside a list. So this package input will be the input to a concatenate layer. I'm calling this output to be concat, and then lastly I'm going to feed this concat as the input to the classification layer and produce the final output. So if we do that, you can see that instead of an addition layer, we are now having a concatenation layer. We were going to have two inputs. Each one will be dimension 512, and then the output from this concatenation layer will be a concatenate output with a dimension of 1024, and then lastly this output will be fed into the classification layer. Next, let's talk about Residual Net. Residual Net is a special kind of deep learning neural network in which two copies are created for a intermediate layer output. One copy will go through the layers just as usual. Another copy will bypass several layers and then combine with the output from a later layer. In this particular example, I'm going to use dense layer number 1 as my intermediate layer and then create two copies for its output. Okay, so the naming convention is that I'm going to name the output for the dense layer number 1 to be first layer output, and then after that all the output will be x_2, and before the classification layer we are going to combine x_2 and this first layer output together, feed that into the classification layer and then get the final output. Let's go to the Jupyter Notebook and see how we can create a model that we just talked about. So we just need to follow the naming conventions. The inputs will be fed into the flattened layer, which will create x_1. x_1 will be fed into the first dense layer, which will create first layer output. This first layer output will be fed into dense layer number 2, which create x_2, and x_2 will be overwritten by dense layer number 3 and dense layer number 4. Finally, we are going to add first layer output and x_2 together. This summation will be the input to the last classification layer, which create the final outputs. And then lastly, we are going to call this keras.model by passing the input parameters and then output parameters to create our model. And I'm naming this model to be functional API residual model. Again, you can see the schematic illustrations by calling this .plot model, so that you can see the output from the dense layer number 1 will have 2 copies. One copy will go through dense layer number 2, 3, and 4. Another copy will bypass that and then directly combine with the output from the dense layer number 4. This combined output will be the input to the last classification layer. Once we build the model, we can again compile it and train it, make predictions, etc. Next, let's talk about multi-output model. So in some cases, we can have multiple outputs in our deep learning model. This slide shows the schematic representation of our examples. So first thing is that we are going to feed input into the flattened layer, which produce the output. I'm calling it x_1, which will be fed into dense layer number 1, dense layer number 2, and dense layer number 3. At dense layer number 3, the output will have 2 copies, which are both third layer output. First copy will go through classification layer number 1, which will produce output number 1. The second copy will go through dense layer number 4, which produce x_2, which will be fed into classification number 2 and then have the output number 2. Let's go to the Jupyter notebook and then see how we can create that. So we just need to follow the naming conventions. The inputs will be fed into the flattened layer, which produce x_1, which will go through dense layer number 1, dense layer number 2, and dense layer number 3. The output from the dense layer number 3 will be the third layer output. One copy of the third layer output will directly go to a classification number 1, which will produce outputs_1. Another third layer output will go through dense layer number 4, which produce x_2, which will be the input to the classification layer number 2, which will then output the output_2. To call the keras.model, we are going to feed the input parameters as usual, but because we have 2 outputs, we need to package our 2 outputs inside a list and then specify the output parameter to be equals to this entire list. Once we build the model, we can again check the schematic representation of the model. So as you can see, the output from dense layer number 3 will be split into 2 copies. The first copy will go through classification number 1. The second copy will go to dense layer number 4, which will then go to classification number 2. After we create the model, we can compile the model, but because we have 2 outputs, we need to specify 2 loss functions. And when we train the model, we need to make sure that we are passing 2 outputs that are packaged inside a list. Similarly, for validation dataset, we need to pass in 2 outputs that are packaged inside a list. But other than that, everything works as usual. When we are trained a model with multi-outputs, it will output the loss functions for both layers and then the metrics for both layers as well. Next is the multi-input model. In this model, we are going to create 2 inputs. First is the input_number 1. The second is the input_number 2. Input_number 1 will be fed into flattened layer number 1, which will produce x_1, which will then go through dense layer number 1, dense layer number 2, and then the output will still be x_1. The input_2 will be fed into flattened layer _2, which will produce x_2. This x_2 will go through dense layer number 3 and dense layer number 4, which will produce x_2. And then finally, we are going to combine those two outputs together and feed the combined output into the classification layer to create the final outputs. Now let's go to the Jupyter Notebook to see how we can use functional API to create a multi-input model. Again, we just need to follow the naming convention that I just talked about in the slides. We are going to create two outputs. The first one is inputs_1. The second one is input_2. Input_1 will be fed into first flattened layer, which will create x_1 as output, which will then go through then serial number 1 and then serial number 2. Inputs_2 will then be fed into flattened layer number 2, which will produce x_2, and this x_2 will then go through then serial number 3 and then serial number 4. Finally, we are going to add x_1 and x_2 together and then treat this combined output as the input to the last classification layer, which will produce the final outputs. Then we need to call this keras.model object by passing the input parameters, and because now we have two inputs, we need to package them inside a list and then pass in the entire list as our input parameters. The outputs are just the outputs. Once we create a model, we can again use this model to see the schematic representation of our model. So you can see that we have input 1 and input 2. They first go through different network in parallel, but then before they fit into the classification layer, we are going to add the outputs together. So we compile the model just as usual. But when we train the model, we need to make sure that we are package our two outputs together inside a list. Same thing when we are passing the validation dataset, we need to make sure that the two inputs are packaged inside a list. Other than that, everything works just as the same. If we want to see the outputs of our model, we can always use the .predict methods, but the .predict method will only gives you the final output. So if we want to see the intermediate output, for example, if I want to see the output from dense layer number 2, then we need to extract this partial model and then build it as a new model. That way, when we call the predict methods from this new model, we will get the intermediate output from this dense layer number 2. So let's see how we can build a partial model from a larger model using functional API. It's actually quite simple. We can simply call this keras.model again, but this time when we specify the input parameters, it will be the inputs to our larger model. We can calling the inputs by using this .input methods, and because we have a multi-input model here, so we need to make sure that we are only extracting one input and then specifying the output by calling the model's getLayer methods. Inside the parentheses, we need to pass in the layer names of our interest, and then finally calling the .output attributes. And as simple as that, we have created a partial model from our multi-input model. If we plot the model and see the schematic representation, we can see that it only goes from input_number 1 to dense layer number 2. Now if we pass in a new input and calling this .predict methods from this partial model, we can have an intermediate output. Another application of these partial model extractions is the transfer learning. Many times people want to leverage the big pre-trained model by only extract the first few layers from this big pre-trained model, and then after that the user will want to add new layers that's more tailored to his own applications. So in this case, the partial model is circled by this red dashed line, and then the new layer is circled by this green dashed line. The partial model is simply the partial model that we extracted from the multi-input model. The output will be x, and then this x will be fed into the new layers, which I call dense layer number 5, and then finally a new classification layer, which will produce the final outputs. Now you have an option to freeze the weights of this partial model if you think those weights are optimum to your applications, or you can simply treat those weights as the initial starting point and not freezing the weights. It is up to the user. Now let's go to the Jupyter Notebook and see how we can implement transfer learning inside the Jupyter Notebook. Again, freezing the weight is optional, but to show you how you can freeze the weight, If you want to do that, you just need to set partial models.trainable attributes equals to false, and then we can treat this partial model as another function. So first, we are going to initiate another input underscore 1. This input underscore 1 will be the input to the partial model, which will produce an output x. This output x will then be fed into this new dense layer number 5, which will produce a new x. This new x will be fed into the new classification layer, which will produce the final output. So after we specify these operations, finally we can call this keras.model by specifying the input parameters and the output parameters. I'm calling this model to be transfer learning model. We can call this .plot model to have a schematic representation of our model, but in this case you can see that the partial model becomes a block of itself. We can also print out the summary table by calling this .summary, and again this partial model becomes a layer itself. We can also check the number of parameters, which is 932,000, but the trainable parameters is only 267,000. This is because every parameters inside this partial model layer has been frozen. After that, we can compile it and train it just like what we did before. The last method that we are going to talk about how to create a TensorFlow model is through subclassing. So to do that, we need to create a class. Over here, I'm going to name our example class to be subclassing model, and this class needs to be a subclass of this keras.model class. Inside this class, we need to have two functions. The first one is the init function, and then the second one is the call function, because we want to make sure that we inherit all the methods and attributes from this keras.model class. So the first thing that we need to do inside our init function is to write this line of code, super open and close parentheses, .init open and close parentheses. Inside our init functions, we also need to specify each layer as an attribute to the class. So for example, the attribute of self.flatten will be the flatten layer. The attribute of self.dense_1 will be the first dense layer. Dense_2 will be the second dense layer, etc. And then the classification attribute will be the classification layer. Inside the call function, we will first need to pass in the inputs, and then whatever we are return will be the outputs to our model. Inside the call function, we are just going to specify a set of operations using the functional API. The only difference is that we are going to call the class attributes instead of the actual layers inside our operations. So once we create this class, we can instantiate an instance by calling the subclassing_model open close parentheses, and I'm calling this instance as the subclassing model instance. We then need to specify the input shape of our instance. We can do that by calling this .build methods and then specify our input shape. This time we need to pass in the batch size, and because we do not know the batch size beforehand, so we can pass in none for now. After we build the model, we can also check the summary table, but for some reason we are not getting the output shape if we are building our class through these subclassing methods. If we plot the model, then the entire subclassing model will become a block by itself. But other than that, we can compile the model and then train the model just as usual. If we want our summary table to print out the output shape and then want the plot model to output all the intermediate layers, then we can develop and work around functions inside our class. So we can have these third functions, which I'm calling it to be workaround model. Inside this model, I'm going to first initiate a keras.input object, which I'm calling x, and I'm going to simply return another keras.model instance with the input parameters equals to x, and then the output simply to be self.callX, which is this output here. Now we can instantiate our new subclassing model, and then this time, instead of calling the summary on this subclassing model instance, we are going to call the summary on the subclassing model instance .workaround model. If we do that, then we will get the output shape of our summary table. We can also plot the model not on the subclassing model instance, but on the subclassing model instance .workaround model. So if we do that, then all the intermediate layers will be output. What I have just described is a scenario where we would like to add new methods to our class. Let's now go to another example where we would want to add new attributes to our class. In this example, we want our number of dense layers to be dynamically input by the user. So to do that, we can add a new input from our init methods to be the num-dense layers, and these num-dense layers will be the new attributes of self.numDense layer. And then we are going to specify the self.flatten attributes just as usual. It will be the flatten layers, but the self.dense attribute, instead of a dense layer, it will now become a list of dense layer. And the size of the list depends on this self.numDense layer attribute. Essentially, we are going to run this for loop numDense layer number of times. Every time we run the for loop, we are going to append a new dense layers inside this list. The self.classification attribute will still be the classification layer. And then inside our call functions, we are going to first call this self.flatten layer, but we are going to loop through each element inside this dense list. The number of loop depends on this self.numDense layer. The input to each dense layer will be x, and then output will still be x. And then lastly, we are going to call this self.classification layer. The input will be x, and then the output will be the output. If we do this, then when we are instantiate a subclassing model, we allow the user to specify the number of intermediate dense layers. So in this example, I'm entering 10, build the model, and if we check the summary table, you can see that we now have 10 layers. To recap, in this video, we went through 3 different methods to create a TensorFlow model. The first method is to use keras.Sequencial model. This method is useful whenever our deep learning model is in a simple sequential order. The second method is to use functional API. Functional API is more flexible. Not only it can create a simple sequential model, but it can also create branch layer model, residual net, multi-input model, and multi-output model. It can also use to extract partial model from an existing larger model. It can also be used to do transfer learning. And then lastly, we talk about how to use subclassing to create a TensorFlow model. Subclassing has all the flexibility of the functional API methods, but it also has the benefits which allows you to create new methods and new attributes in your class. This pretty much concludes the video. I will share all the code in my GitHub repository. You can find a link below in the video description. Thank you for watching. I hope you enjoy. If you like this video and you want to see more about it, please don't forget to like and subscribe. Other than that, I will see you in my next video.